back to 345 and made it even better.
Yeah. Okay, coming to you live from a bunker at the foot of the Rocky Mountains, it's Pandemic Physiology. Black, because it's a hallmark color of 2020. If you're not in mourning, there's something wrong. My name is John Waldron. My office number is 235 Physiology, but I'm going to avoid being there as much as I can this semester. My email address, you can always get a hold of me at this address. It's john.waldron@colostate.edu. And you can get a hold of the GTAs, then I'll enumerate those in a moment, at csubms300@gmail.com. This is probably the most helpful of all of the email addresses because this is the one you'll use. Don't use the one that's in the Canvas page. Use this one, and this will get you in contact with the course GTAs. The course GTAs are Michelle Staros. She's the lead GTA, and she's the glue that holds the whole thing together. Then there's Abby Jefferson, and Abby Jefferson is one of the GTAs, and she'll be maintaining the notes. And she's the famous generator of the Jefferson weed tomato that's bearing tomatoes in my garden at this moment. Josh Hayes has been around for years, and he's the stalwart of this crew, and he'll be able to help you, and he's always the backup and ready to go. Davis Ryan Guerrero is here for this semester. This is the first semester. He did it this summer. He's operating the video channel, and he's the one who revamped the entire Canvas homepage, so he's been an important part of this crew. And Madison Propp, who's going to be taking notes, and she will be in the chat box, so you can ask questions of her. And then what we're going to do here is I want to start with the syllabus discussion. And I should say that these outlines that I put on this board are the outlines that we'll cover for that day's lecture. And they're really important. Now, today less so, because we're going to be spending about 20 minutes on the syllabus, and then we'll follow into water. But typically, the outline of each of the lectures will be placed on this board. And if you copy that down, these are the key ideas that will be given in the lecture. And if you become fluent with the outlines that are on these boards, you're pretty well prepared for the exam. So I encourage you to spend time with these outlines, pay attention to them, and spend some time studying from them. Well, let's start here with a discussion of the syllabus. We'll take a few minutes to do this. Basically, what we're trying to do in this course is to provide you with a broad background in human physiology. The course is an upper division course, BMS 300. It's Principles of Human Physiology. And what we're trying to do is give you a foundation of basic physiological principles that you can then carry on to other courses. This is a prerequisite courses for any number of other courses at the university, and we think that it provides a kind of foundation that leads you into a number of other courses, particularly advanced courses at the 400 level. And so we encourage you to spend some time with this material and learn it, and we think that by some of the tricks that we have tried to incorporate into this course, that this will help you with any number of other courses later on in your academic career. There are prerequisites for this course. There's a semester of college chemistry and a semester of college biology. where you get that semester isn't so important, but it's important to have the general information from those courses. We're not going to spend a lot of time in here balancing equations for chemistry. We're not going to be spending a lot of time on taxonomy that you may have seen in BMS, in Life 102. But what we will be doing is we'll be using those foundations to build further foundations in biology. And so it's really important to have some fluency in the basics of biology and chemistry. There's an optional textbook. If you would like to have a textbook that you can use as a kind of reference text, then I suggest Vander's Physiology. Don't go to the bookstore and buy it. I don't think you need a new copy. Get one that's out of print. Go to one of the online booksellers and get one that's been out of print for a while. You can get them fairly cheaply. And then don't read it like a novel. Use it as a reference text. If there's something in the lecture you don't understand, if there are figures that don't make sense to you, go to the reference text, use the index, then find that general idea in the index, go to the paragraph or two that's dealing with that idea, and just read that. Don't read it like a novel. It'll wash over you. So use it sort of judiciously. There is a required ebook. The required ebook has all of the pre-lecture quizzes in it, and it has all of the objectives in it, and from those objectives there are links that go to figures with narratives, and those figures are the ones I'll be presenting in class. I don't teach very much from a form of PowerPoint slides. I teach mostly from the board, and then I'll supplement those with figures, most of which will be found in the ebook. And I certainly encourage you to get that ebook. You should have gotten an email from the bookstore, and you should be able to simply opt in and get the ebook. If you don't want the ebook, you'll have to opt out. And if that's the case, then you won't have access to the ebook quizzes that we'll discuss here in a moment. When you study for this course, it's a slightly different course than other courses you've taken in most cases. When you study for this course, don't memorize everything. You're going to see that there's a tremendous amount of information that's coming at you day in and day out. You can't memorize all that information. What you have to do is learn the stories. And I'll try to teach this course in the form of a series of stories. And then you need to become fluent in those stories. And then when you take the exam and you read an exam question, you don't simply say, oh, I know what the answer is from the answer list. You look at the question and you say, what's this question trying to get at? What's the point? What's the idea it's trying to illuminate? Then you call up in your internal dialogue the discussion you have had with these different stories, either from the outlines in the board or from the lecture itself. And by going back and becoming fluent with these stories, then you answer the question on the exam from the story. It just makes it a whole lot easier, and it's a different way of learning. And it requires, I think, a different skill set. So you can't just memorize things, you have to connect the dots. It's not, I think that if you can learn how to learn in that fashion, it will help you in any number of other courses. And so we're trying to encourage you to do that. There are all of these GTAs and office hours we'll discuss in a moment to help you be able to learn in that fashion. The lectures will be live streamed. Well, of course, we're all online this semester. There are over 600 students in the class, and any class at CSU over 100 students is online. So this course is going to be entirely online, but in order to try to make it as much of a lecture course as I can, to try to make it as close to a live lecture course, what we're going to be doing is we're going to be streaming the video at 11 o'clock. For those of you who can't make the 11 o'clock lecture, it will remain open until 1. What this means then is you can go to the link in your Canvas page into the live streaming, then tune into the lecture. And if you start at any time after 11, between 11 and 1, you can start from the beginning. And there will be a GTA in the chat box that will be answering questions throughout that time. That way, I think we can do the best we know how of making this as close to a live lecture as possible. Now, having said that, all of these lectures will be archived. And it takes a little while for the machinery at Google to get these compressed, but usually around 2, 3 in the afternoon, I'll be able to go get that link and then put it into a file in Canvas. So then you can watch those archived videos. I encourage you to watch these live. as much as you can, I think you should watch them live, in part because you've been trained since you were 5 years old to go to a class, be in a class for that period of time, and concentrate and focus on that material. There's a real pitfall in these courses when they're online, in that the videos are archived. You can go and watch those videos whenever you want, and so there's a tendency to put off watching them until the weekend, thinking, oh, I'll catch up on Saturday, and you never do. And so I really encourage you, if you can't watch the lectures live as streaming video, find a time in the day that you designate as when you're going to be in lecture. It could be 8 o'clock at night, but find a time and always use that time to go to lecture so that you're disciplined enough to maintain the lectures and keep up with them. Otherwise, you can fall behind awfully quickly in this class. There are a whole bunch of learning opportunities in this course. What we have tried to do is provide a number of different tools for you to learn this material. And many of these tools have associated with them extra credit points. So the first one is going to be homework. Now the homework will be coming out of the ebook. Now what we've tried to do with the ebook quizzes, we can't do it the first week because we're beginning from the beginning, but in the ebook, what we're going to try to do is we're going to try to have you have quizzes that presage what's going to be given the following week. What I mean by that is you'll be asked to read a certain number of objectives and passages and answer questions on those passages. That will be material that we have not yet covered in a lecture. So this will introduce you to the language, introduce you to the ideas, introduce you to the figures before we actually get to the lectures themselves. It's a kind of priming. One of the things that we've found over the years in this course is that there's a language issue, that there's a lot of new language in this material. And what will happen is I'll say a word that I've been using for years, but it may be new to you. And because it's new to you, you have this sort of pause in your mind trying to figure out what that word means. And then the lecture continues onward while you're trying to figure out the meaning of that word. So what I think is the real advantage of the quizzes in the ebook is you've reviewed the material beforehand. You have some idea what the language is and what those words are, and what the figures are going to be. And that's what the ebook quizzes are about. Now, you can get extra credit points from the ebook quizzes. There are 12 possible points on 14 different quizzes. And so you can get a total of 12 extra credit points that will be added to your grade after the exam grades have been determined. And we'll talk about grading in a minute. After each lecture, there's an after-lecture quiz. They're only worth, I think it's a tenth of a point or so, but in aggregate, over the 59 lectures in the course, they'll be worth 8 points. Those 8 points are all extra credit points. Those quizzes will open up at 1 o'clock on the day of the lecture and remain open until midnight the following day. So you have plenty of time to go in and take those quizzes. But again, it's one of these learning issues that psychologically you're much better off to take on that information, answer those quizzes, watch the lectures, and go to this material immediately rather than waiting till late in the next day. What the after lecture quizzes are meant to do is to familiarize you with the material in the lecture, ask you some fundamental questions about that material so that you go back through the material and study it a little bit so you can get those answers. And again, there are about 8 points available for that. The third extra credit possibility is through tutorials. The tutorials are run by undergraduate students. The tutorials are students effectively who are in this course a semester or two, maybe a year or two ago. They have struggled through this course, and they're the students who have done well in the course, and they have volunteered to lead these tutorial sections. They volunteer to no small extent because the way they're learning the material is to further review it, and that's the way they'll solidify it for later courses. But they're also there to help you. All of these students like the course, they like the material, and they like teaching. And so they'll lead these discussion sections, they'll lead these tutorials, and they're meant to be small group discussion sections where you'll get together with some of your peers and 1 or 2 tutors or 1 or 2 of these undergraduate TAs and discuss the material. All of this is going to be through Zoom. All of this is going to be through Zoom in breakout rooms. So there's none of this going to be in person. So that will be organized through the tutorials, and you can find the tutorials on a link from the homepage in the BMS 300 site. There will be a calendar there showing all of the dates of the tutorials, all of the tutorial leaders, and you can choose one of those. I suggest that you find one that fits your personality, one that fits with how you learn, and work with those tutors and other students. Now, the recitation is a separate class. BMS 200 is a separate course. It's a 1 hour, it's a 1 credit course that's independent from 300 in the sense its grading is independent. But it's dependent upon 300 in that the material that we present every week in BMS 300, those weeks worth of lectures, will then be reviewed by the GTAs and in the recitation section. All of these recitations are going to be held on Zoom. And we found that in Zoom we can generate breakout rooms. So we can break the larger group, which is usually 30 or 35 students, into smaller groups of half a dozen or so and have students work together. We think this group work and this collaboration is really important for learning, and we're going to try to have you work through some of this experiential learning in the recitation. So we've planned this out. We did a little bit of this last semester. We did some of this summer, and the recitations are, I think, an important part of the course, but of course they're optional. For those of you who are in the online section, we just added today that BMS 200 online section. I thought it had already been up there, but it's just been put in today. So if you're interested in this, go to your online website, BMS, the CSU BMS, I'm sorry, the CSU online, and look up BMS 200. And if you're interested in that, you can enroll in this recitation. There will be a series of Canvas-based quizzes in 200, and there'll be a series of discussion sections. I'll let you read the academic integrity piece. Exam information. There will be 4 unit exams in here and a final. Each of the 4 unit exams will be 2.5 hours long. All of these exams will be online, and you will access these exams through Canvas. They'll be proctored through Canvas. For those of you who are in the online section, they'll be proctored through Respondus. No, I'm sorry, they'll be proctored through HonorLock. Each of the exams has 32 questions that are multiple choice, and then each of those are worth 2.5 points. Then there'll be an additional 20 or more points that will be in fill-in-the-blank questions. So we try to divide the exam into sections which are multiple choice and typically graded then by the computer, and then a series of fill-in-the-blank questions. The fill-in-the-blank questions are basically stories, and I think they're useful because what they do for you is they help you learn how to learn from the stories, and then whenever you read one of the multiple choice questions, you don't read it as a multiple choice question so much as you read it as a fill-in-the-blank question. And you say, what's the idea this was drawn from? You start the fill-in-the-blank question and you answer the question from that story. And the fill-in-the-blanks in themselves are simply stories. Typically, we'll have about 28 blanks that are worth 20 points, so there's some extra credit on each of the exams associated with those fill-in-the-blank questions. Again, you'll have 2.5 hours to take the exam, but the exams are going to be open on Wednesdays, and check the schedule that's at the bottom of the syllabus to see what days those will be on, what dates they will be on. All of the exams will be on Wednesdays. They will open at 1 o'clock after Wednesday's lecture. Wednesday's lecture will not be on the exam, only Monday's lecture of that week will be on the exam. And the exam will be open from 1 p.m. until midnight, and you need to take the exam during that window. If you're in the online class, that window is a little broader. For the online students, because many of you are working, that window is a little broader. Check the syllabus for when those are open. And again, they'll open. Check the syllabus for when those are open, because I may make a mistake on that. Now, be sure, because the exam will close at midnight, to have the full 2.5 hours on the exam, what you need to do is start the exam by 9:30. Those of you who have accommodations and students for the students in the SDC, please let us know, and we'll add time in on the exam. Makeup exams. This is a pretty hard and fast statement in here about the fact that there are no makeup exams. If you have a valid reason for missing the exam, and heaven knows this semester there are going to be a million of them, you may be quarantined, you may be sick, there may be someone in your family who's sick, please let us know and we'll make accommodations. We're not going to be too hard-nosed about these exams. We're going to try to get them done as quickly as possible, though, following that time window. You should look at the website, the HTTPS COVID recovery, for information about how to deal with COVID in your courses. I'll let you look at that. If you're auditing the course, please let me know. I'll have to add you into Canvas, and there are rules for that, and we can talk about it. If you're completing an incomplete grade, please send me an email so I can add, so you can be in Canvas. If you're completing an incomplete grade, also send me an email so I can give you instructions on how to re-access the ebook. If you've taken the course before, I'll give you a web link that will give you, so where you can explain to the publisher that you're retaking the course, and that because you're retaking the course, you'll get a new access code free of charge. How we do the grades in the course. The way we do the grades in the course is that there are 4 unit exams and a final. And of these 5 grades, the lowest will be dropped. But if you look at this table, you'll see that the course grade is based on a total of 500 points. So typically what will happen is we'll have the 4 unit exams, each worth 100 points. That's 400 points. And the final is 200 points. Well, immediately you say, well, that's 600 points. Well, what we'll do is if your lowest grade is on one of the 4 unit exams, we'll drop that lowest score. The final will then count twice. And so you have your 3 unit exam scores and your final counting twice. If your lowest grade in the course is on the final, then we'll count your 4 unit exams and count the final only once. Then that will be the total number of points you have from the exams. That exam score then will be the basis for your grade in the course. And what we'll do is we'll determine the grade cuts based on those 500 points. Then once the grade cuts are made, we'll then, subsequent to that, add in the extra credit points. So you can get a score in this course without doing any of the extra credit. But I can't tell you how many times I've looked at students right at the border, right between an A and a B, or a B and a C, or a C and a D, and I think, why didn't they do the extra credit? Those extra credit points would have pushed them up into the next grade. So these extra credit points are really valuable, even though you don't need them to get your grade, and even though they'll be added in after the grades are determined. The grading is typically 90, 80, 70, 60. Now, some of the exams I will reserve the right to add some extra points to bring the mean up to the low 70s. Now, if the exam scores are already in the 70s, I won't add any points. But if they're below 70, if the means are low, I will normalize each of the exam scores. The exam scores then won't, so those will be effectively curved for each of the exams, and there isn't much curve at the end of the course. We do that in part so that if you're not doing well in the course, you have an idea where you stand so that you can W withdrawal at the date halfway through the semester. The final page is basically a list of the lectures, who's giving the lectures, and the topics, and then the exam dates. I give about 90% of the lectures in here. Dr. Bauma will come in at the end of the semester. He gives all the lectures on reproduction. I know nothing of reproduction. I sometimes wonder how I had children. The final exam will be on Thursday of exam week, and it will open at 8 a.m. and close at 8 p.m. And then finally, there's the final table that will show the total number of questions on the exam and how they're broken down into parts of the exam. That final exam is cumulative, and it's required. I think it's an important aspect of the course. It brings the ideas we've discussed all semester into one place in the final exam, and many students find that their real understanding of the course is pointed out to them in the final exam. So are there any questions that I should deal with? Okay, so where we're going to start is we're going to spend some time today talking about water and its components. Water fundamentally is the elixir of life. All of life on the planet depends upon ion solutions in water. We'll see that we're going to separate these solutions from one inside and outside of a cell across a phospholipid bilayer, a membrane. But in order to understand that, we have to spend a little bit of time walking through the very fundamental ideas of what water is. We'll talk a little bit about the components of water. Of course, water contains 2 hydrogen atoms and 1 oxygen atom, and that gives it a molecular weight of 18, 16 from the oxygen and 2 from the 2 hydrogen atoms. We'll put these molecules together and show the idea of covalent bonding. The covalent bonding is where the electron in the shell of the hydrogen is shared with the 6 electrons in the outer shell of oxygen. That's going to be a covalent bond. Now, water is unusual, and we know water is unusual. We know water is liquid at room temperature in spite of having a molecular weight of 18. If we look over here at this table, and don't memorize these numbers, I'll never ask you about numbers, but I think it's instructive to walk through this small table that shows nitrogen. Nitrogen is the predominant gas in air around us. 79% of the air around us is nitrogen. It has a molecular weight of 28. The other 21% of the air around us is oxygen. It has a molecular weight of 32. Despite these heavier molecular weights than water, the boiling point for nitrogen is minus 196 degrees. The boiling point for oxygen is minus 180. And in the extreme, helium, which is a noble gas, having a molecular weight of 4, has a boiling point of minus 269 degrees centigrade. This is 3 degrees Kelvin. But look at water. Water has a molecular weight of 18, and yet its boiling point is plus 100 degrees. What is it about water that makes it so different from these other molecules? And the answer has to do with the hydrogen bonds. Because of the construction of water from 2 hydrogen atoms and 1 oxygen atom, it's said to have a dipole moment. And we'll see that this is the way the electrons are shared within the molecule. Because of the way that electrons are shared, there is a dipole moment on that molecule. And because of the dipole moment on the molecule, even though its net charge is 0, it has a positively charged end and a negatively charged end. That means it's polar. And that allows it to interact with other molecules of water in something known as hydrogen bonding. We'll see that the hydrogen bonding is equivalent to tiny magnets between the water molecules, holding the water molecules together. Those electromagnetic interactions are extremely brief, only on picoseconds or so, and then the molecules switch around and find another water molecule to interact with. But in so doing, they are living with one another, and because of these electromagnetic fields, they live close to one another and allow water to be liquid at room temperature, between 0 degrees and 100 degrees centigrade. But this dipole moment on water also has other important implications. It allows for ion solubility. All of life occurs in an aqueous solution of salts. And this dipole moment allows negatively charged ions called anions to go into solution, as well as positively charged ions called cations. The ones we'll discuss are in sodium chloride. We'll talk about how sodium chloride can go into solution in water and then will be randomly distributed in the water column. The concept of the random distribution of these ions is really important to all of biology. We're going to see over and over and over again that we're going to employ the concentration difference and the random walk of the molecules with respect to that concentration difference being important for the movement of ions and molecules. We'll see it when we talk about nerve cells. We have ions moving across membranes. We'll see it in the respiratory system. We talk about oxygen and carbon dioxide moving across epithelial cells in the lung. We'll see it in terms of movement of water in the kidney. All of this, the random walk of molecules. And we'll spend a lot of time talking about that. Then finally, we'll end here, perhaps it'll be tomorrow or Wednesday, but perhaps we'll get to it today, and that is to talk about sodium chloride in water. And we'll do a thought experiment. We're going to drop some sodium chloride into water. We've all done this at the dinner table. Shake a little bit of sodium chloride into a water glass, and it goes into solution. And we'll talk about why that is, and bring it back to the idea of the dipole moments on water. And we'll talk about how in water, sodium chloride, because of its highly positively charged sodium and highly negatively charged chloride will go into complete solution, and it will completely dissociate into sodium ions and chloride ions, and we'll talk a little bit about the implication of that dissociation. But let's first talk about components of water. We all know this. It's H2O. That means there are two atoms of hydrogen and one atom of oxygen. Now, if we look at the oxygen, I'll put this in red. And we look at the electron shell of the oxygen, the outer electron shell contains 6 electrons. I'll put a couple pair up here. Two, 4, 5, and 6. Let me put them down here actually. Then here in blue is going to be a hydrogen atom. Now, you recall from your basic chemistry that hydrogen contains a proton and an electron. It's the simplest of all of the elements in the universe. It's made of a single proton and a single electron. Well, this electron here in blue can be shared with the electrons on oxygen. And there'll be another hydrogen over here, which has an electron, and its electron, true, can be shared with the electron shell, the outer shell, and oxygen. When these electrons are shared, this is called a covalent bond. The stable state for oxygen is to have 8 electrons in this outer shell. 1, 2, 3, 4, 5, 6, 7, 8. 2 of those are donated by the hydrogens, 1 each of these hydrogens. The rest come from the oxygen itself. Now, in oxygen, there are going to be 8 protons, and there will be 8 neutrons. Whereas the hydrogen itself is simply a proton. Because of the mass of the nucleus of this oxygen atom, the electrons are drawn more tightly to the oxygen than they are to the hydrogen. What this means then is if we think about these electrons are in a cloud. Dr. Heisenberg told us that we don't know exactly where they are. We don't know what their momentum is, but we know that they're somehow out here in a cloud. We can't predict exactly where they are, but they're in an average space. When we look at the structure of water, we find that because of the charge of the protons and the mass of the oxygen atom, these electrons are spending more time around the oxygen than they are around the hydrogen. Because the electrons have fundamentally been borrowed or stolen from the hydrogens, this end of the molecule has a slight positive charge. And we denote that by showing a delta positive, delta positive. And here on the oxygen molecule, oxygen atom, we say that this is a delta negative. Now when we look at this, we think this is a hard and fast positive site and a hard and fast positive site, hard and fast negative site, but that's not really true. Because of the way the electrons are in this amorphous cloud out here, whizzing around in this region, but spending on average more time with the oxygen, this end of the molecule has a this end of the molecule has a negative end, this end of the molecule has a positive end. We can simplify this view by saying, here's an oxygen, and here are the 2 hydrogens. This line represents the covalent bond, and it has a positive charge out here on the hydrogen and a negative charge on the oxygen. This simple arrangement, the sharing of the electrons with the covalent bond, but much of the time of the electrons spending around the oxygen, giving it a net negative, and I shouldn't say negative, giving it a negative end, and the hydrogens giving it a positive end, has real implications for the structure of water itself. And I'll try to show that over here. If we imagine a myriad of water molecules, and in a liter of water, I think it's a million molecules of water, but we're going to just look at a few of them, where we have these hydrogens. They're positively charged, linked to the oxygen, but this has a partial negative charge on it, where the hydrogen has a partial positive charge on it. Because of this negative charge, the oxygen down here, with its partial negative, will be attracted to the positive end of the water molecule here. This is said to be a dipole moment. Because of the dipole moment, saying that this is the generally positive end of the molecule and this is generally the negative end of the molecule, these dipole moments can interact. It's as though they're tiny magnets. It's as though you have two refrigerator magnets being attracted by their opposite poles, being held together here by this hydrogen bonding. Now, to be sure, these hydrogen bonds that are the magnetic fields holding the water molecules together are not nearly as strong as the covalent bonds. But these hydrogen bonds are strong enough to keep these molecules attracted to one another. And in the liquid state, these molecules are being attracted to one another. These hydrogen bonds are very, very short-lived. They only last a few picoseconds. This end of the molecule will switch around and find another water molecule to interact with, and constantly all of these molecules are living with these hydrogen bonds for very brief periods of time. Now, as we increase the energy in that water, as we increase the thermal activity by, say, putting on a pot of coffee, putting water in a kettle, you increase the thermal activity here until there's so much thermal activity that the thermal activity is strong. The thermal activity breaks these hydrogen bonds, and these molecules will go off as a gas. That's when you boil water. The other end of that spectrum, if we take energy out of the system and we reduce the amount of energy, and the dwell time of these hydrogen bonds gets longer and longer, eventually these will crystallize into water. They'll still move a bit, but they'll be crystallized in a tetrahedral structure of water. As a sidelight, one of the things that makes this molecule unusual, in addition to being liquid at room temperature and having its hydrogen bonds in this orientation, is that because of these hydrogen bonds and the way they form when water freezes, the ice actually expands. You know that intuitively. You know if in the wintertime the pipes in your house freeze, the water is going to expand as it forms ice, and it's going to break the pipes. This becomes important for biology on the planet because when the ice expands as it freezes, as the water expands and as it freezes into ice, it now decreases its density, and therefore ice will float on the top of water. That's why we have icebergs. And it's why the planet is not just an ice ball. If water would freeze and sink, then we'd be living on an ice ball. But in fact, because water freezes and floats, and it's on the surface, it can then be irradiated and warmed up and converted back into water. But for the most part in here, we're going to be thinking about what's going on with these dipole moments and these hydrogen bonds, because it's this charge on the water molecules which allows for ion solubility. And it's this charge on the water molecules, the polar nature of water, which allows ions to go into solution and make the salt solutions that are essential for life. So do we have any questions to there? Okay. Well, if not, let's go to the right-hand panel and think a little bit about what happens when we put sodium chloride into water. So we're going to do a thought experiment here, and this is meant to be a beaker. And I'm going to begin here with the idea that we have a water surface here. This is the surface of water. And so this is called the air-water interface. Just to give you some idea of what's going on at the air-water interface, I will take a moment and talk about the hydrogen bonding that's occurring in the water. So you can imagine right at this air-water interface, there are these oxygens with their hydrogens. And all these dipole moments are going to be interacting with one another. So there will be hydrogen bonding between these two. This provides a lot of electrostatic interaction between these water molecules at the air-water interface. This is a remarkably strong series of interactions. And just to illustrate that, if you go out this afternoon and you sit beside a pond someplace and you watch the insects, many of those insects will be something called water striders, sometimes known as Jesus bugs, because they walk on the water. And they walk on the water because they have these very fine hairs or setae at the end of their legs. And they can actually stand on the surface tension of the water. And to illustrate this, it's kind of cruel, but it's an interesting thing to do. You can catch one of these water striders, take them into the house, and put them on a bowl of water on your kitchen table, and they will stand on the water just fine. But if you add a little bit of dishwashing detergent, where the detergent then will get in between the water molecules and separate the water molecules, make them farther and farther apart so that their interactions are less and less strong, you reduce the surface tension and the water strider will sink to the bottom of the bowl. I don't intend for you to do that, but it's a good illustration of how surface tension is important. And we're going to run into surface tension later on when we talk about the respiratory system. But for now, just know that it is the interactions of the dipole moments on water which allows for surface tension at the water-air interface. But the next thing I want to talk about is the concept of ion solubility. And in the concept of ion solubility, I need my green marker here. At the bottom of this beaker, we're going to just put a box. And I'm going to label this as sodium chloride. This is basically a sodium chloride crystal. And we have magically dropped this into the bottom of the beaker. And we put a particular amount in here. This is going to be 5.84 grams. And this volume is going to be 1 liter. Now, in the sodium chloride crystal, and I won't get into the details here, but these are all packed in a cubic crystal fashion so that each sodium ion lines up with a chloride ion. And the sodium ion and the chloride ion are charged. They're charged because the chloride, in order to fill up its valence shell, takes on an extra electron. The sodium, in order to fill up its valence shell, loses an electron, so it's positively charged. But these charges, the positive charge on sodium, the negative charge on chloride, allow these highly charged particles to interact with the dipole moments in water. So you can imagine that the water molecules are in here bouncing about. The thermal activity of the water molecules is bouncing around in here, and they're colliding with the sodium chloride crystal. It's a bit of an exaggeration, but you can imagine this energy of the water molecules bouncing around here, chipping off these individual ions from the sodium chloride crystal. And in so doing, what will happen is the sodium ion will be liberated from that sodium chloride crystal and come out into solution. Let me do it this way. The sodium ion will come out into solution, along with its counter ion, the chloride ion. Now recognize that there's this charge on those ions. And there's also the charge on the water. The negative end of the water molecule is going to orient itself so that it sidles up to the sodium ion. Here's our hydrogens pointing out the other way. And the negative charge, the polar end of the water molecule, is going to interact with the positive charge on the sodium. And this is going to generate something known as a shell of hydration. All of these sodium ions, which are a type of cation, orient to the negative end of the water. Similarly, these chloride ions are going to orient in such a way that the positive dipoles of the water molecule will try again. The positive ends of the water molecule, the hydrogens, are going to orient to the chloride atom. So in blue are the hydrogens connected to the oxygen. And the hydrogens connected to the oxygen. These positive ends on the hydrogen will now interact with the negative charge on the chloride. And now these again will form a shell of hydration around the chloride ion. So now these sodium ions and chloride ions are going into solution because they're interacting with the dipole moments on water. Chloride interacting with the positive dipole moment of the hydrogen, and sodium interacting with a negative dipole moment on oxygen. Now this number, 5.84 grams, was not chosen randomly. It turns out that the molecular weight of sodium chloride is 58.4 grams per liter. Because I've moved the decimal place, this is going to generate a 0.1 molar. You can read this as 100 millimolar sodium chloride solution. But there's an additional caveat to this, in the sense that the sodium ions are going to almost completely dissociate from the chloride ions. And since we were using 100 millimolar sodium chloride, what will happen is we will generate 100 millimoles of sodium ion and simultaneously generate 100 millimoles of chlorides. So the total number of particles in here, we add the two together, we have 200 milliosmoles of ions, 100 of which milliosmoles is from the sodium ion and 100 from the chloride ion. So we have completely dissociated this sodium ion and chloride ion, which was in the crystal, into the water solution. And the final thing I'll end here with is for you to imagine how these sodium ions and chloride ions being buffeted about by the water molecules are going to be eventually randomly distributed in the water column. And we'll begin our discussion on Wednesday with this idea of the random walk of ions in the water column and how that can be then used to move ions down a concentration gradient.